Right. Thank you for your patience. My name is Preben Nyeng. I'm working with Energinet.dk. I don't know if everybody knows Energinet.dk, but we're the Danish transmission system operator. It means that we have the overall responsibility of operating and maintaining the high voltage transmission grid in Denmark. What I'm going to tell you about is a project called EcoGrid EU, and as you just said, it's a demonstration project, but it's also a research project. And I'm actually going to focus more on the research part. But first, let me get rid of this. Okay, we put it up here. A very short summary of what is this project. It's called Large-Scale Smart Grids Demonstration of a Real-Time Market-Based Integration of DER and DR, so Distributed Energy Resources and Demand Response. It's granted under the European Union's 7th Framework Program. It has a budget of 21 million euros, out of which roughly half is financed by the European Commission. There are 16 partners, and it's a quite large number of partners to bring together. And it's because we cover quite different areas of this project. It's quite broad, but I'll tell you more about that in a moment. There's a demonstration ongoing, and then there's a research part. The demonstration will include 2,000 customers, which is quite a lot. It's quite a challenge to get so many customers in a very limited area, namely Bornholm, the Danish island. It involves market design, ICT infrastructure, customer products, customer behavior studies, and the whole lot. So it's really a very complete smart grid project in that sense. And hopefully what we get out of it is some knowledge about how we can really move smart grid forward in Europe, and some experience with operating demand response on a real-time market. It has its own webpage. You can go and find more material there. So the partners, they're all listed here, and we can divide them in 4 groups. We have some industrial partners. They're mainly providing the technology and doing the development part of the project. It's Siemens and IBM and Landis & Gyr who provide the meters. Then we have a lot of research institutes. At DTU we have the University of Tallinn, CFEM and AIT in Austria. And then we have a bunch of system operators like me, from distribution companies as well as transmission companies. And then we have some independent consultancy companies, experts in the smart grid area, Technalia, ECN, and TNO. And by bringing all these competences together, it's the idea to really do something useful. The demonstration is going to take place on Bornholm, and it's not just because we thought, well, there's a nice island in the middle of nowhere, let's do a demonstration there. It's actually a quite well-considered choice. First of all, if we look at the island as such, there's a very high penetration of renewable energy sources, mainly wind power. So in that sense, it's a good picture of how the whole country will look in 10, 20 years. And then there's been a history of research projects on this island doing smaller demonstrations. And there's a political commitment on the island and among the population on the island to this movement towards a green future. And it's very important when you want to recruit 2,000 people. It's roughly 5% of the population. If you want to recruit that number of people, it requires there's some commitment. The customers I'll start out now with saying a little bit about the demonstration, and then I will move completely away from the demonstration. So just to finish the demonstration part, the 2,000 customers will be divided in 5 groups, 5 types, ranging from customers who are actually not involved as such. All we do is we give them a smart meter so we can monitor their power consumption. But they don't do anything. So we call them a reference group. In the other end of the scale, we have the fully automated companies with a lot of equipment to really automate the whole lot, so to say. And in between, we have different degrees of automation involved. And what we're hoping to see is how important is this automation compared to how much can people do just by changing the way they use power. So now I will move on to the market part, sort of why we're here. And the first question that pops up is, why does it have to be a real-time market? Why can't we just include these resources in, for example, the day-ahead market? Well, there's a number of good reasons for that. First of all, it's a good way to meet these challenges we're facing when we're changing the whole system to be based on renewables. We'll see more of a demand for flexibility in the system, both on the consumption side and on the production side. And the real-time market is a very good way to activate this flexibility. Then there's another thing, that is, if we can make a real-time market and make that work, we actually automatically include the demand response also in the day-ahead markets. So if we do that, we can do everything. So it's to set the ambitions high, because then we get the whole package at once. It's very important to include demand in the power markets. You probably know that today we have, well, the power markets, they work, but there's only competition on the production side. There's basically no competition on the demand side. And it means that the markets could actually be working better than they do if we included the demand in the markets. We would get more competition, and at the end of the day, would get a lower cost of the whole system. Then an illustration or a positive side effect of doing this is seen from our point of view. Today, if we look at this picture, you see the mouse? Yes. We have sort of a chain of markets. Time scale moves towards now down here. And as we move back in time, we have different markets taking care of that. First, we have a financial market. It operates with a time horizon of years. I haven't included that. Then there's a day-ahead market, some intraday, and finally the regulating power market. It's the last market we have before we switch completely to what we can call non-market-based control. It's called direct control here. But it's basically fully automatic. It's done by controllers at the large power plants. Finally, we have the mechanical inertia, also at the power plants, to really keep the system balance at the sub-second level. But there's a line here that separates the markets from the control part. And what we want to do is we want to move that line closer to real time by introducing a new market platform. And the reason for that is we believe that markets basically are better at allocating resources than these pre-allocated resources participating in the automatic control. So it's simply to increase the efficiency of the system. Then, as I mentioned, we sort of have two projects in one. At least we have two tracks in the project. We have a demonstration part and what we could call a research part. But it's based on the same concept. So what we'll do is there's some research going on on how could this concept be implemented in the long run, in a large, wide deployment scenario. But at the same time, in 2012, we launched the demonstration on Bornholm, where we want to demonstrate as much as we can of this concept. What we cannot do is we cannot create a new market in the real life. There's no way we can do that. So what we need to do is I call it a virtual reality. We need to create a perception of a market in the present. It's a little difficult to do that, but it's a challenge. But now I'll shift to the research part, because that's actually where the real market design is going on. So this market concept, what should it do? Well, it should be economically efficient. Goes for all markets. There's no need to have a market otherwise. What that means is it's based on the core idea of presenting in real time the real price of electricity, defined as the marginal production cost at that time. And it fluctuates. Of course it does. So we want to present this information to everybody in the system in real time. Then it should be a transparent concept. We want the prices to be public, because that's the only way we can derive retail products from this price that is essentially a wholesale system information. It should have a high time resolution. The markets we know today, they have a time resolution of 1 hour. The resources, energy resources we know of, they fluctuate a lot within 1 hour. So we thought it doesn't really make sense to have the same price for a full hour if the wind power goes like this in that hour. Then, apart from the time resolution, the delay of publishing the price should be very short. Because what we do today is we actually create the prices for tomorrow, today, which means that forecast errors affect the prices in real time. And if we want to get that information out, we need to wait until we know for certain what is actually the price right now, what is the wind power production, etc., so we can send that information out. Finally, and as I will show in the end, this is probably the toughest part. When we started this project, we had an idea that it should be possible to handle local prices so that congestions in the system could be handled with a price. So what I've said so far is pretty general to any approach you can take to this problem. But now I'm moving into the actual design of the EcoGrid market concept. So the fundamental idea of this concept is actually this picture. We have a cloud of distributed energy resources. It could be anything that has the ability to respond to a price signal. They all interact with the power system, the electricity network. And what the TSO is doing up here, he monitors the system. Then he checks, is the system in balance? Let's say he does that every 5 minutes. And then when he realizes that it's no longer in balance, he will change the price. If there is a surplus of power, he will lower the price. If there's a deficit, he will increase the price. And then he sends out this price signal to all these devices. And hopefully they do something. If the price goes up, some of them will reduce their consumption or increase their production to bring the system back in balance. And then this is repeated every 5 minutes. So you can consider it as a closed-loop control system where the price is the control signal. It's very different from what we know today, because today we have auctions only. All the power markets we know of are basically auctions, where we send in bids with our marginal cost or our willingness to pay for a certain volume, and then there's a market clearing price. This concept is a little different because there are no bids, so the TSO has to find the clearing price only based on the physics of the system. And the big question is, what does the TSO do when he realizes there is an imbalance of, say, 10 megawatts? How will he convert that to a price signal? If he doesn't have a bid, he doesn't have a list of resources he can dispatch, he simply has to base the price on previous experience. So there's a lot of, this box, it contains a lot of algorithms to predict what will these do as a response to a certain price signal. It's the only way this system can work. So that was sort of the control system point of view, where we make a closed loop and then everything is nice. We have a control signal, we have a feedback. So what's the problem? The problem is that at the end of the day, if anybody should respond to this, they should actually be billed with this price. They should pay this price for their electricity, or if it's a production device, they should be paid this price. How can that happen? Because the TSO is definitely not dealing with individual consumers, but now he's sending a price to the individual consumers. To understand how this can work, we need to look into how is the settlement done in the power system. And this is roughly how it works today. This is what we can call the ex-post settlement of the final consumption and production. Before this picture, there is the whole chain of markets, of course, where we exchange power. But this is what happens after the fact. So there's a hierarchy. We have the TSO as the spider in the web, or here he's located at the top. Then we have these BRPs, they're balance responsible parties. And balance responsible doesn't mean that they're responsible for maintaining the balance of the system. It means they're responsible for, financially responsible, for any deviations from their schedules. I'll show a picture in a bit that clarifies this, but just to underline that they are not responsible for maintaining the balance of the system, because there can only be one that is responsible for that, and that's the TSO. Under each BRP, we can see some suppliers, and the supplier is also called a retailer. It's him who handles the connection with the customers and settles with the BRP. And then we have, of course, the consumers, and here are some production devices. This all works very nicely, and what we're doing now is we're sort of introducing a disturbance. It should be a positive disturbance because it should help us balance the system. But in this picture, it's basically a disturbance. There's a signal now going from the TSO, bypassing all this in the middle, directly down to the consumers. How can this work? It can work like this if we can make it happen, because what we actually want is, if we have some production devices, wind turbines, who create an imbalance in the system, we would like them to pay actually the consumers to correct this balance. And the only connection between these two is through the BRPs, via the TSO, another BRP, a supplier, and then back to the consumer. So there's a whole change of settlements that should work for the money flow, the cash flow to be right. Now it gets a little complicated. For those of you who are completely familiar with how the power system, power markets work, this will be trivial, but I expect maybe some of you are not familiar with that. So I'll just introduce first the wholesale link. it means the link between the TSO and the BRP. That's what I call the wholesale level. Down here we have the retail level. So what goes on is we have some markets, as I said, L-spot, L-bas, it's the day-ahead and the intraday market. That's what we can call a trading phase. But we need to be aware that what we're trading is basically not, I know this will provoke some, but it's not a physical commodity. It's not what we're trading. We're trading a contract for either supplying or consuming that commodity in the future. So basically these markets are forward markets. It's all they are, and what we get out of that is a schedule, a set of contracts defining who should do what in the future. Then in the present, when the future becomes the present, something happens, and it's rarely what we defined in our contracts. Something different may happen. We call this difference, we call it balancing power. It's also called imbalances, financial imbalances. And they're settled with those are the ones settled with the BRPs. The sum of the contract and the differences, the balancing power, equals the physical consumption or production. And we meter that with the power meter. Now, this equation, there's a plus here, so it would indicate, and there's a logical flow. This is the past, this is the present, and this is ex post. But what happens in reality is, first we trade, then we do something, but we don't know what we're doing in real time. Then we get the meter readings, and then we do the math and say, okay, this balancing power is the difference in reality between the meter readings and the contracts. But mathematically, this is how it works. Now, the interesting thing is that, as you can see, there's an arrow here coming from the ex post part to the real-time part. It means that in real time, we don't know the price of our actions. If a power plant chooses to generate out of the blue an extra megawatt, it doesn't know what he'll be paid for it. Likewise, if a consumer with a heat pump suddenly decides to switch it on, he doesn't know how that impacts the settlement between the TSO and the BRP. That's a challenge, because it actually means that the incentives to behave according to the real-time price are hidden, because we only publish what is actually the real-time price after the fact. As you can see, I have hidden something here. It's the EcoGrid model, and I will reveal it to you in a minute. But before I do that, I will illustrate this setup with a few examples. A production unit, he sells something in the day-ahead market. Then he only produces this amount. The difference is that he buys this in the operating phase. Likewise, another production unit, he sells this part in the day-ahead market. He generates this volume. The difference is this part. So by definition, he's selling that in the real-time market. And likewise for the consumption. What I'm trying to do here is illustrate that even if you're a consumption device, you can sell power. May sound odd, but if you bought it in the day-ahead market and you don't use it, you're effectively selling it in real time. So here is the EcoGrid version. As you can see, the trading phase is exactly the same. So we don't envision anything to change with the day-ahead markets or the intraday markets or the financial markets for that matter. The difference is here in the real-time phase, the operation phase. What we want to do is, instead of getting this price after the fact and then telling people what they should pay, we want to tell them in advance. The next 5 minutes, the price is this value. then everybody can behave according to this price signal. We don't have a word for this. We could call it EcoGrid power. It's basically still imbalances in the sense of financial imbalances with the BRPs. Furthermore, you can see this box, it's now chopped up in smaller values. It's just to illustrate that instead of hourly metering, we're switching to a metering with a higher time resolution. The price, as I mentioned before, is set by the TSO every 5 minutes. He doesn't have any bids he can look into. He needs to base it on expectations, forecasts of the response. And if he's very wise, he will also look 5 minutes ahead and try to predict the imbalance. So there's a lot of work for people interested in predicting things in this project. And then there's a technicality. The price should be published somehow. We envision it could be a web service because what's important is that machines can read this price. Evidently, no one would be interested in visiting a web page to read a price every 5 minutes. But we could show it to humans so they could respond to it if they want to. Now, this is a numerical example of how this could work. It's a lot of information on a slide, I know that, but if you want to revisit it at a later point, you can do that. Basically, it illustrates this setup with the trading phase, the operation phase, and the settlement phase. And we have, in addition to what we saw before, where we only had this part, we also have the power pool included. So I've created 2 examples. First, a down regulation situation, and then the symmetrical up regulation situation. And I won't go through all the numbers, but if we look at the day-ahead phase, we can see that what the BRP is doing, he bids for what he thinks would be the consumption, 100 megawatt hours. Then in real time, the price is lower, so we consume more down here, 125, because the customers are responding to this price signal. And then in the settlement, this extra 25 megawatt hours are logically supplied by the TSO, but of course there's another BRP providing these 25 megawatt hours. So it all adds up. Vice versa, in the up regulation, he does the same day ahead. He contracts for 100 megawatt hours. But due to a high price in the real-time situation, we consume less. So in the settlement phase, we're selling back 25 megawatt hours to the TSO. So the 2 numbers that are interesting is this 5,000 and 4,500. Together it's 9,500. I can show you the numbers here. If we add this together, what we get is, so to say, a reduction, because what we would have paid was 10,000. So the customer saves 500 euros altogether, of course, but it's split out on individual customers. And the TSO loses 500, but this money comes from another BRP. So it's the flow you saw before, moving from the wind turbines through one BRP, through the TSO, the next BRP, and down to the customers. What you can also see is the BRP ends up with a big 0, and the same does the supplier. So this basic setup creates a path of value actually from the TSO to the customers. And the TSO, even in this path, is actually just the man in the middle, because we have created a link all the way down to those creating the imbalances. And that's a nice feature of this setup. Now, then the logical question is here, then how does the supplier make money? How does the BRP make money? Well, of course, they add markup, like they do today. They don't settle wholesale prices with their customers. But this is just to illustrate the changes of the EcoGrid model. Skip these. So this pretty much sums up this architecture. In addition to what we had before, which was this focusing on the contracts and the billing, we have the price signal, or the information needed to create a price signal goes into this price generator. It's published at a market platform, and then it's sent out. I've already mentioned this, but for this to work, of course, we need the electronic meters. We need those meter data to be fed back to the TSO's data hub. So we have 3 very different roles of the TSO, but they're all involved in this setup. So where are we now, and what are the next steps? As I said, this was the research part. We cannot demonstrate this on Bornholm because we cannot, if I go back to this one, we cannot do this. We cannot send out this price signal in the real power system. We need to keep it in a closed system for a number of good reasons. And we can also not affect the settlement between the BRP and the TSO. So we're creating this virtual reality, and it's really focusing on the consumers. That's the interesting part here. So we are playing that the consumers are in a setup where this market was implemented. So we're sending real-time prices to the consumers. They're getting a lot of gadgets to control their consumption. We have a lot of research and questionnaires going on. How do they experience this? Are they happy? Are they not happy? And so on. It's all ongoing. Then on the research side, we're starting some system studies, because what's interesting, especially from the TSO's point of view, is if we send out these price signals every 5 minutes, how does that affect the balance? Can we reliably predict the response? How does it interact with the faster reserves that I showed in the picture, and stuff like that? And then finally some replication studies, because as I also mentioned, it's actually the idea to hopefully be able to roll this concept out. But there are very different market setups in Europe, and if we want to do this, we need to investigate quite thoroughly how it could work in the different setups. What I've focused on is the Nordic setup, but around Europe we'll find some differences. To summarize or sort of perspectivize this concept, some of you may know the Dangrid report. It's called Smart Grid in Denmark 2.0. And the thing about this report is it's published by the TSO and all the DSOs, the distribution system operators, together. So it's really what all the system operators in Denmark have agreed on. So this is sort of the playing field for future markets. And what we can see down here, there's a new market for flexibility. And it's mainly aimed at providing the grid companies, the DSOs, with a tool to alleviate congestion in their own grids. It means that this idea, as I mentioned in the beginning, with locational prices in the distribution grids, it's probably not going to happen, at least not in Denmark, because the DSOs have very clearly stated they want a different setup. They want a setup with firm bids, where they can trade with commercial partners, balance responsible parties. So if they activate a bid, they have a very firm commitment to a response in the other end. They're not interested in this setup where you send out a price and then there is some uncertainty on the response. So that's how congestion management in the distribution grids will be handled. So where does EcoGrid fit? It actually fits up here what we call existing markets. Existing markets in this sense is the TSO markets, which is the wholesale markets for energy in the large system. And actually that's what EcoGrid is in its basic form. It's yet another market for balancing the system, but it's on a shorter time scale and with a higher time resolution. So EcoGrid does fit, but not the part about the locational pricing. That was what I intended to bring today. If you have any questions, I think we have a little time.
Do you have any questions?
Thank you for your presentation. Very nice overview. I was a little bit concerned, or perhaps I don't completely understand, but with these 5-minute responses, it has to be completely automatic, as you said, like it's machines that's doing it. I could be a little bit concerned about like what's sometimes called herding or lemming effects in the stock market. We've seen like automatic systems for buying and selling, leading to huge imbalances sometimes. So I just wanted to hear if you have had, any. When prices are only at the 5-minute resolution, they have to vary quite quickly. And are there checks and balances that make sure that you don't suddenly have everybody selling? I see suddenly millions of heat pumps are switched off at the same time, and then the response is much bigger than it was supposed to be, and quickly you have to have something back and so on. How is that? How do you avoid lemming effects in the system?
We don't do anything actively to avoid that. But the reasoning is that if you look at 1 million heat pumps, they're quite diversified. And each of them is in a different situation, temperature-wise, heat capacity, power to heat, and so on. So it's like you could say, why would they do that? Why would they? There should be a gain for them to speculate, and it's very difficult to see that in this setup.
That's the point. There's also no point in doing it in the stock market, but it's happened anyway.
Okay. I'm not.
So it's behavioral economics. It might because of these automatic selling and buying systems. If there's certain checks in it, this is not about incentives as such. It's about how the system responds to price signals. It's how quickly will it check back and so on.
No idea. But it's an interesting study.
Question there? Yeah.
Thank you. Very nice overview. Just to the last picture here, you say on the TSO side the 5-minute prices, and generally also the demand response will be servicing the TSO in fixing the system balance. And as the previous speaker remarked, there could be very strong reactions on the distribution side, which, as you mentioned, could challenge the DSO level where they have congestion. Now, this setup says that there will be services paid for by the grid companies to relieve this congestion. Is there any discussion about how would the TSO pay for creating problems for the DSO? There's two players playing each other, competing against each other, designed into the system, and there's very straightforward game for whoever wants to play it to play these two monopolies against each other. So is there any considerations in this direction?
Not really, no. But I would again say I don't. Maybe it's because I'm with the TSO, but I don't see it as a big problem, in the sense that these heat pumps would be there anyway. So if they are in a peak, we cannot make them peak anymore. If you know what I mean, we can create more peaks, of course, if that incurs some costs for the DSO. I'm not sure it's a real problem, but
it has been several studies that have shown that if you don't have the specific pricing, you have a certain load distribution. If you increase the pricing, you have you reduce the utilization factor, so you concentrate the peaks, and thereby increase a much higher grid requirement with demand, which will reducing the utilization factor of the distribution companies, thereby increasing their costs, and thereby forcing them into buying new services.
Yeah, but
I mean that's very.
As you said, we have a pretty clear division of TSOs and DSOs, and who's doing what, and where we each collect the money for what we do. And I mean, we could settle this between the TSO and the DSO, then the TSO would have to increase his tariffs, or the DSO could increase his tariffs. But I think it belongs more logically on the DSO side, anyway.
No, but it's not system efficiency. It's not a market design that leads to system efficiency. I mean, this logic is sort of clear. And I mean, just saying that we all collect our money just means that again the end customer will pay more, and new market participants who will see this opportunity will rip off more of the system. This is a flaw in the system design.
No, it's not a flaw that some customers pay more. That's I wouldn't say it's the intention, but I think it's a natural side effect that if we put a price tag on flexibility, some will get a lower bill and some will get a higher bill.
No, everyone will get a higher bill.
No.
Can I perhaps ask you to continue this discussion afterwards, and maybe conclude with one final question, because we have only 1 minute before we...
Everybody's saying not the higher to need a very stupid implementation of such a system. But one thing I'm wondering about is it a real possibility that the National Data Hub will be able to handle finding price signals? I cannot see that coming.
Sorry, I didn't.
Is it a real possibility that the National Data Hub can handle 5 minute price signals? I don't think so.
Well, I'm not an IT expert, but I guess it's data, and there are many ways in which you can store data, and I think it's a lot of data. It's many more times what we know today, but there are other systems that handle even more data. So from an IT perspective, even though I'm not an expert on that, I would say that's not the biggest problem.
Okay, so I think we should conclude now and say thank you once again.